We are investigating a consequence of the conservation of potential vorticity, Rossby waves. We've seen how a change in f can be expressed as the beta plane approximation, which allows us to examine the dynamics of flows with large latitudinal extent. So we'll begin by recalling the expression for potential vorticity and the assumptions that we have made in order to develop this, that is, that the flow is inviscid, it's thin and wide, and it's rapidly rotating. The equations describing the horizontal motions that we use to develop the potential vorticity expression are the expanded, time-dependent rotating momentum and continuity equations. These describe the flow, and they also describe the small perturbations that are carried by the flow. It is often useful to think of the flow as containing lots of small fluctuations that average out to have a zero mean contribution to the flow. These fluctuations can be thought of as waves for their zero mean component, or having small velocities, such that we can neglect the nonlinear advection terms that are shown here in red. We rewrite the top two equations without their advection terms, and we make the substitution for f as the beta plane approximation. We then use the hydrostatic approximation to rewrite the pressure gradients in terms of surface height anomalies eta, for which the x direction is the acceleration in x minus the beta approximation times v is equal to the gravity times the surface height gradient in x, with an equivalent equation in the y direction. Note here that we can recognize the geostrophic balance in these expressions. That is, these expressions contain hydrostatic geostrophic terms here in black, and terms that we call ageostrophic here in blue. Remembering that the flow is to first order geostrophic, so we can use the geostrophic balance to approximate the ageostrophic horizontal velocities and describe them in terms of surface height anomalies eta. So we substitute these back into equations 1 and 2 for the small terms. We want to rearrange these new equations for u and v, finding that v is equal to gravity on the reference Coriolis parameter times the x gradient of the surface height minus gravity on the reference Coriolis parameter squared times the y and time derivatives of the surface height minus beta y times gravity on the reference Coriolis parameter squared times the x derivative of the surface height, and an equivalent equation for the u velocity. Again, the blue terms here are small, and we refer to these as the ageostrophic velocities. These describe the behavior of the small amplitude wave perturbations that are superimposed on top of the balanced geostrophic flow, which you should recognize here in black. Remember that we started with three equations, and the third equation, the continuity equation, we have neglected up until now. We want to integrate the continuity equation over the depth of the fluid h, giving this depth h times the horizontal divergence plus the vertical velocity at h minus the vertical velocity at 0. Now, the vertical velocity at 0 is 0, that is, there's no flow through the bottom boundary. And at h, the vertical velocity is simply the rate of change of the free surface, d eta by dt. So we have the rate of change of the free surface plus h times the horizontal divergence is equal to 0. We now want to substitute the geostrophic plus ageostrophic velocity terms for u and v back into the horizontal divergence part of this new equation. Gravity on f squared is a common term that we can pull out, leaving this expression for the depth integrated continuity of geostrophic plus ageostrophic velocities. Now we can expand this out. We can already see that there will be some common terms that cancel. So we are left with these three terms: the third derivative of eta by dx squared dt, the third derivative of eta by dy squared dt, and a term with beta times the x gradient of eta, which survives because of the product rule. We can pull out the time derivatives from these first two terms and substitute the Laplacian operator for the second spatial derivatives of eta. We can also define r, the Rossby radius, as the square root of GH on F, and substitute this back in, giving the time derivative of eta minus the Rossby radius squared times the time derivative of the Laplacian of eta minus the Rossby radius squared times beta times the x derivative of eta is equal to 0. This is the planetary Rossby wave equation, and it describes the motion of small perturbations on top of the background geostrophic flow.